When doing advanced process control, one is often going to hear reference to a model. Welcome back. We're going to take the next couple of minutes and put all of this into perspective. I've taken the liberty of putting a simple little diagram on the screen itself. Now, in advanced process control, or the acronym APC that we're often going to encounter, we like to represent our processes using a first order plus dead time model. First order plus dead time model. You might come across that acronym. This really captures how a process responds dynamically to changes in its input. It's going to be defined by three very important parameters. The very first one is going to be our process gain, often represented by the letter KP. And the process gain can be described as the steady state sensitivity of the process. It's going to tell us how much the output will change for a given change in the input. Often I go and do the calculation where I'd say that the change in the process variable divided by the change in the output that caused it is going to give us this process gain. A high gain is going to speak about the fact that a small input change can produce a large output change in the process. And just the opposite, a low gain says that an input change is going to have a very weak effect on the process. So the role of the process gain in advanced process control is to determine the magnitude of the controller's response. Accurate gain estimation is essential for model predictive control, for feed-forward compensation, as well as for tuning. That's the first of the three aspects that we need to have. The second important aspect is going to be our time constant. Once again, nothing that you haven't heard of before in my videos. This often is going to get represented by the symbol lambda, or otherwise I just like to put in TC. It is the speed of a process. It is the time required for the process to reach 63.2% of its total response after a step change. And of course, we ignore any dead time. Now, as you would know, in my case, I often say near enough is good enough. We don't have to work to the third or the second or the first decimal point. I just like to have a look at approximately how long it takes to get to 2/3 of the way. 67% is going to be very, very close to 63.2%. So a small time constant is going to represent a fast process, and a large time constant is going to represent a slow process. In the case of advanced process control, we're going to find that the time constant determines how quickly the controller must act. It's going to influence prediction horizons, which you'll get to hear about in the MPC controller. It's going to influence tuning aggressiveness as well as our stability margins. And this brings us to the third component of my model, and that is going to be the dead time. I just like to use the lettering TD, but you might find that people have got different symbols that they may go and use for that as well. Now, dead time is often referred to as our delay or our transport lag. This is the period of time that elapses from when an output has changed until you and I can see a noticeable response in the process variable. It's often caused by transport delays or sensor lags or analyzer delays or physical separation. We have said on a number of occasions that long dead times can make the control more difficult, and we've also said that dead time cannot be fixed. You either design it out of the process, or otherwise you need to go and compensate for it. So dead time, that third component of mine, is going to be absolutely critical in model predictive control because it affects the prediction accuracy and the constraint handling. It's also going to limit achievable performance in PID loops and required specialized strategies, such as the Smith predictors and the dead time compensation. Right, so in a nutshell, my model is going to be made up of 3 important components, and we need to make sure that we are going to address each of those. The better your model, the better your control is going to be. Stay tuned and watch out for all of the new videos. We're going to try and cover as much material as possible as a basic introduction. Thank you and goodbye.